Welcome back to the Deep Dive. Today we're plunging into a world that often seems just beautiful and serene, a place to escape. But beneath that surface, there's this constant story of flux, immense power, and, well, some pretty significant challenges. Our planet's coastlines. We've pulled together a really fascinating stack of sources for this deep dive. We've got everything from, captivating travel guides showing off stunning beaches, all the way to rigorous scientific explanations of oceanography and some critical reports on coastal erosion and climate change.
Yeah, our mission today is really to understand that intricate dance between the land and the sea. We'll explore how coastal landforms are actually created, the powerful processes shaping them, and also get into the urgent issues they're facing now. It's kind of a journey from those picturesque spots to the real cutting edge of environmental science.
Exactly. So whether you're maybe dreaming about your next beach trip or you're just curious about the forces at play right where the land stops and the ocean starts, you're definitely going to want to stay with us. Okay, let's start unpacking this. When we think of a beautiful beach, what usually comes to mind, often it's that blindingly bright white sand, sparkling turquoise water. Our sources have some absolutely unforgettable examples. Think about Shipwreck Beach in Zakynthos, Greece. Those dazzling white limestone cliffs, that rusty shipwreck right on the sand, pretty iconic. Or, completely different, the Black Sand Beach in Iceland, formed by waves just pulverizing volcanic rock. It's got those amazing basalt columns. You've probably seen it in Game of Thrones or Star Wars. And then there's Anse Source d'Argent in the Seychelles, famous for its huge granite boulders, pinkish sand, exotic birds, just stunning. But beyond just how they look, what else draws us in?
Well, what's really insightful here, I think, is how this natural beauty connects so deeply to human life. It's not just pretty. Our sources point out that about half the world's population, that's roughly 3.5 billion people, live along coastlines. And yeah, mild climates, great seafood, easy transport, those are factors. But there's maybe something deeper, too. That feeling of escape, recreation, maybe even cultural significance. Coasts have always been hubs. So this raises a really important question. How do we actually define this dynamic interface? Our sources help clarify this.
Yeah.
Think of the shore, that's the really active zone, right? Between the lowest tide and the highest point hit by storm waves. Constantly changing.
Okay, so the shore is where the action is.
Exactly. Then the coast is broader. It extends inland, basically as far as you find features that are clearly ocean-related.
Right.
And the coastline, that's the specific line marking the boundary between the shore and the coast. It's like the landward limit of the biggest storm waves.
So it sounds like none of these are fixed lines on a map, really. The shore moves daily with the tide, and the coast itself is changing. Our sources really stress that these aren't static places. Changes can happen over, years or decades, not just millions of years, which is incredibly fast, geologically speaking.
That's the key takeaway, I think. They are incredibly dynamic, this idea of a stable coast. Mostly a myth in the long run.
Okay, so this dynamism, it gets really interesting when we talk about what beaches are actually made of.
Yeah.
Sand seems simple, but it's not just sand, is it?
Not at all. It's fascinating, really. Beaches are basically composed of whatever local stuff is breaking down, weathering rocks, mostly. So Florida, for example, often has that pure white or beige sand. That's largely quartz, which is really durable.
Okay.
But then you go to volcanic areas like Iceland or Hawaii. Boom, you get black sand beaches. That's from basalt, volcanic rock breaking down.
Right, totally different source material.
Exactly. And tropical beaches, they can have a lot of biological stuff mixed in shells, bits of coral. So the color beige, white, pink, black, even red or green, sometimes it tells you a unique geological story about where that sand came from.
Wow. And all this diverse material is just constantly being reworked by the ocean's power, right?
Immense power. Waves are incredibly destructive. Just think about the weight of water. They exert huge pressure. It's called hydraulic action. It can force apart soil, even splinter rock, just by the force of the water being pushed into cracks.
It's like a relentless hammer. And you mentioned the sandpaper effect earlier. Is that the abrasion part?
Precisely. Abrasion is when the waves pick up sand, pebbles, other bits of sediment, and just hurl them against the cliffs and rocks, grinding, scraping, chipping away over time like giant wet sandpaper, yeah.
And sometimes the water itself dissolves the rock.
Yes, chemical weathering. Okay. Seawater can dissolve certain types of rock, and this can actually be sped up by changes in ocean pH, with more CO2 in the atmosphere.
Okay, so it's hitting it, grinding it, and dissolving it. A constant attack.
Pretty much.
And the sand doesn't just get pushed straight in and out. It moves sideways, too. This longshore drift.
Yes, longshore drift or longshore transport. This is crucial. Imagine a wave, the swash, washing up the beach at an angle. It carries sand with it up at that angle.
Right.
Then the water, the backwash, drains back down, usually straight down the slope, perpendicular to the shoreline, pulling sand with it.
So it's a zigzag motion.
Exactly. That zigzag movement creates a current flowing parallel to the shore or the longshore current. And these currents are powerful. Our sources say they can move millions of tons of sediment along a coastline every year.
Wow. That totally explains why you can be swimming and suddenly find yourself way down the beach after just 10 minutes. You're literally riding that current.
You absolutely are. And this dynamic also causes big seasonal changes on beaches. Like our sources talk about California beaches. In summer, with generally lighter waves, sand builds up, making wider, sandier platforms called berms.
Okay, the nice wide summer beach.
Right. But then winter comes with heavier storm waves. They erode the beach more, pulling sand offshore, creating narrower beaches, and often forming underwater sandbars called longshore bars. It's a constant cycle.
It really is a living system, constantly adjusting. So with all this relentless action, erosion, transport, deposition, it's no wonder coasts look so different around the world. Our sources group them broadly into erosional and depositional types,
Yeah,
right? Each with its own set of features.
that's a good way to think about it, yeah. Erosional shores, you often find these where the land is being pushed up, tectonically speaking, like the U.S. West Coast. They're typically marked by well-developed cliffs, and you get features like headlands.
Headlands, those are the bits that stick out further into the sea.
Exactly. They take the brunt of the wave energy, and because they stick out, waves attack them from multiple sides. This energy can carve out sea caves at the base of the headland, just tunneling into the rock. And if a cave erodes all the way through a headland, or two caves meet back to back, you get these magnificent sea arches, like those amazing ones off Portugal you sometimes see pictures of.
Incredible natural sculptures. What happens when an arch finally gives way?
Gravity wins eventually. The top collapses, leaving behind an isolated pillar of rock standing in the sea. That's a sea stack.
Oh, okay.
And even the stack keeps eroding, eventually becoming a lower sea stump, which might disappear entirely below the high tide line.
Wow. Any other cool features on these erosional coasts?
Oh, yeah. You can get blowholes, where waves force water up through a vertical shaft from a sea cave to the top of the cliff. It shoots up like a geyser during big waves.
That's dramatic.
It can be. And you also see marine terraces. These are basically old, flat, wave-cut benches, platforms, eroded by waves at sea level that have then been lifted up above the water by tectonic uplift, like steps marking former sea levels.
Fascinating. So that's the erosional side, coasts being carved away. What about the depositional side, where stuff builds up?
Right, depositional shores. You see these often where the coast is gradually sinking or where there's just a ton of sediment being delivered, like the U.S. East Coast or the Gulf Coast. Here, the dominant processes involve depositing sediment, building out the land.
And this is where we find things like barrier islands, like Miami Beach, or the Outer Banks in North Carolina, those long sandy strips offshore.
Exactly. Those long, narrow islands of sand running parallel to the main coast. They're classic depositional features. And they often shelter calmer bodies of water behind them called lagoons.
What's their main role, geologically speaking?
Well, crucially, barrier islands act as a natural first line of defense. They absorb a huge amount of wave energy during storms, protecting the mainland behind them. They're incredibly important ecosystems, too.
Makes sense. What other depositional features do we see?
You get things like spits. Those are ridges of sand that are attached to the mainland at one end, but then extend out into a bay or across an estuary entrance.
Kind of like a sandy finger pointing out.
Sort of, yeah. And sometimes a spit might grow all the way across to connect an island to the mainland. That's called a tombolo. And then you have deltas. These are huge, often complex deposits of sediment where major rivers meet the ocean or a lake. Think of the Mississippi River Delta. It's built this massive, kind of bird's foot-shaped landmass out into the Gulf of Mexico entirely from river sediment, constantly changing shape.
Wow, the scale of that is huge. And then there are estuaries. We hear that term a lot.
Yes, estuaries are really unique and important coastal environments. They're basically semi-enclosed coastal bodies where fresh water from rivers mixes with salty ocean water.
So a mix of fresh and salt, or the different kinds.
Definitely. Our sources break them down into four main types based on how they form geologically. It tells you a lot about the region's history. First, you have coastal plain estuaries. These are maybe the most common type. They're essentially drowned river valleys. Think of Chesapeake Bay. Sea level rose after the last ice age and flooded the lower parts of existing river valleys.
Okay, so rising seas created them.
Then you have fjords. These are spectacular. Long, narrow, very deep inlets with steep sides carved out by glaciers. When the glaciers melted and sea level rose, these deep valleys flooded. Think Norway, parts of Canada, Chile, New Zealand.
Right, those dramatic glacial valleys.
Then there are bar-built estuaries. These form when barrier islands or spits build up and partially cut off a lagoon from the open ocean. Common along gently sloping coasts like the Gulf Coast of Florida. The barrier acts like a dam, creating the estuary behind it.
Okay, and the last type.
Tectonic estuaries. These are formed by geological activity, specifically faulting, where land has dropped down, creating a basin that then floods with seawater. San Francisco Bay is a prime example of a tectonic estuary.
Interesting. And how the fresh and salt water mix varies too.
Oh, absolutely. It depends on the river flow, the tides, the shape of the estuary. It can be vertically mixed, pretty uniform top to bottom, or highly stratified with fresh water flowing out on top of denser salt water below. Or sometimes you get a distinct salt wedge where the salt water pushes inland along the bottom underneath the outflowing fresh water, creates really complex conditions.
So it's clear, coasts are incredibly dynamic, beautiful, varied, but it feels like we're now shifting into a part of the story where things get, well, more challenging. A lot of the pressures they face seem directly linked to us, to human activity. Is that fair to say?
Unfortunately, yes. While erosion is natural, our actions are significantly accelerating it in many places. Coastal erosion is a huge issue.
And one of the biggest drivers our sources point to is rising sea levels. Right? They mention an average rise of 3.3 millimeters per year now, up from 1.4 in the 20th century. What's behind that acceleration?
It's primarily two things. One is straightforward. Melting glaciers and land-based ice sheets, like Greenland and Antarctica, are adding vast amounts of water to the oceans.
Right, meltwater.
But the other factor, which is really significant, is thermal expansion. As the ocean water warms due to climate change, the water itself expands. Warmer water takes up slightly more space. When you scale that up across the entire volume of the ocean, it adds up to a major contribution to sea level rise.
And the potential impact. Our sources mention something quite stark. If all the ice melted.
Yeah, the numbers are staggering. If all the remaining ice on Greenland and Antarctica were to melt, global sea levels could rise by something like 230 feet or about 70 meters. Obviously, that's an extreme, long-term scenario, but it gives you a sense of scale. Even much smaller rises have huge impacts. It means low-lying coastal areas, beaches with gentle slopes, they're extremely vulnerable to being permanently inundated or rapidly eroding away.
And layered on top of that is the issue of storms becoming more frequent and intense.
Exactly. Stronger storms mean bigger waves, more powerful storm surges, heavier rainfall. All of this hits the coast harder. It washes away beaches faster, batters cliffs, causes more frequent and severe flooding in coastal communities. It's a double whammy with sea level rise.
And this leads to something called coastal squeeze. What's that?
Coastal squeeze is a really critical concept. Imagine a natural beach or wetland. As sea level rises, it would normally migrate inland, shifting its position.
Okay, it adapts.
Right. But what happens when we've built roads, houses, seawalls right behind the beach? The beach can't move inland anymore. So it gets squeezed between the rising sea on one side and our fixed developments on the other. The result, the beach narrows, habitats like marshes get drowned, and eventually they can disappear altogether.
We're literally trapping them. That has huge implications. And we're also messing with the sand supply itself.
Dams trapping sediment.
Yes, that's another major human impact. Rivers naturally carry sediment down to the coast, which replenishes beaches and deltas. But when we build dams upstream for hydropower or water storage, they trap a lot of that sediment behind them. So less sand reaches the coast, starving beaches of their natural supply and making them erode faster. It disrupts that whole longshore transport system we talked about.
And then there's just straight up pollution. Unfortunately, yes, beaches and coastal waters are often dumping grounds. Trash, plastic debris, oil spills, chemical runoff from agriculture and industry. Even sewage overflows from cities during heavy rain. It all contaminates the environment, harms marine life, closes beaches, and degrades those vital ecosystems.
The sources give some really concerning real-world examples, like Skipsea in the UK, built on soft clay, losing over 10 meters of cliff in just 9 months. That's terrifyingly fast.
It is, and that's one of the fastest eroding coastlines in Europe. It highlights the vulnerability of certain geologies. Even harder rock, like the famous chalk cliffs at Beachy Head, they're eroding to maybe 60 centimeters a year on average, but big chunks can fall off suddenly.
And this puts homes, infrastructure right in the firing line.
Absolutely.
Yeah.
Properties, railway lines, roads, valuable farmland, they're increasingly at risk. Our sources mentioned Fairborn in Wales, where the official advice is basically that the village can't be saved from coastal flooding and erosion in the long run, maybe by the end of the century. Imagine being told your community might have to be abandoned. These are incredibly difficult, painful situations.
So given this immense power of the ocean, the rising sea levels, the increased storms, what can we actually do? How do we protect these coastlines? Is it just about building bigger walls, or are there other approaches?
That's the multi-billion-dollar question, really. Historically, the go-to approach has been hard stabilization. Think concrete seawalls, lines of rock armor, or groins, those barrier walls built out perpendicular from the beach to trap sand.
Right, engineering solutions.
Exactly, and they can protect what's directly behind them, for a while at least. But the problem, as our sources really emphasize, is that these hard structures often make erosion worse somewhere else, usually downdrift. They reflect wave energy, scour the beach in front of them, and eventually they can fail. Nature often finds a way around or under them. It's often a case of nature eventually winning.
That's a powerful thought. So fighting fire with fire or water with concrete isn't always the best long-term plan. Are there softer alternatives, ways to work with nature?
Yes, and that's increasingly where the focus is shifting, towards soft solutions or green infrastructure. One really common one is beach nourishment, sometimes called beach replenishment. You see this a lot in places like Florida, including Miami Beach.
Mhm.
They dredge sand from offshore, often from those longshore bars, and pump it onto the eroding beach to widen it.
Building the beach back up.
Essentially, yes. It's expensive, you often have to repeat it every few years, and finding suitable sand can be tricky, but it maintains the beach for recreation and as a natural buffer.
What else falls under soft solutions?
Well, there's relocation or managed retreat. This means physically moving buildings, roads, infrastructure further inland, away from the eroding edge. It allows the coastline to behave more naturally, but as you can imagine, it's often socially, politically, and economically very difficult to implement. People don't want to move.
Understandably. And planting vegetation, does that help?
Absolutely. Planting native dune grasses or other stabilizing vegetation on dunes and cliffs is a key green approach. The roots help bind the sediment together, trap windblown sand, and build up natural defenses. It's about restoring the ecosystem's own resilience.
Okay, so specific projects like nourishment or planting,
Hmm?
are there broader strategies communities use?
Yes. Coastal management plans usually involve deciding on a broader strategy for different stretches of coast. Our sources outline a few main options. There's hold the line. That means committing to maintaining or upgrading existing defenses to keep the shoreline where it is now, often used for cities or critical infrastructure.
Okay, defending the current position.
Then there's managed realignment, sometimes called managed retreat. This is where you strategically allow the shoreline to move inland to a new, predetermined position. It might involve breaching old seawalls to create new salt marshes, for example, which can then absorb wave energy. It's about working with the inevitable change in a planned way.
A strategic withdrawal, almost.
Kind of. Then there's no active intervention. This basically means deciding not to build any new defenses or maintain existing ones and letting nature take its course. Often happens in sparsely populated areas.
Letting go.
Right. And finally, very rarely there's advance the line, which means building new defenses seaward of the existing line. Usually very expensive and environmentally controversial, like land reclamation projects.
These sound like incredibly tough choices, especially the managed realignment or no active intervention options when people's homes are involved. The UK forecast you mentioned, 750 properties potentially lost soon, even with spending. Maybe 80,000 long-term, if not.
Yes.
It really brings the dilemma into sharp focus, doesn't it? How do we possibly balance our desire, maybe our need, to live and work right by the sea with these undeniable, powerful, and accelerating natural forces? The costs, economic, social, emotional, of trying to protect everything versus the costs of letting go or relocating, they're immense. It impacts homes, livelihoods, farmland, infrastructure, entire communities.
We've definitely taken a deep dive today. We've gone from the sheer beauty and allure of coastlines, explored the incredible geological forces constantly shaping them, the different forms they take, like cliffs and barrier islands and estuaries, and then confronted the really profound challenges they're facing now, from rising seas, stronger storms, and our own activities.
Yeah, what really stands out is just how dynamic these systems are. They're not static landscapes, they're interfaces constantly in motion. And understanding those complex interactions, the waves, the sediment, the biology, the climate impacts, it's absolutely crucial as we try to figure out how to live with these changes.
It feels very clear that our relationship with the coast is changing, whether we like it or not. And the decisions we make right now about how we build, how we protect, where we retreat, they're going to shape the future of these coastlines for generations.
So, maybe a final thought to leave you with as you picture that boundary between land and sea. If coastlines are defined by constant motion, by this relentless shifting and changing, and our human world often tries to be fixed and permanent, are we ever truly living by the coast? Or are we just experiencing a snapshot, a temporary moment in a much longer, ever shifting dance between the land and the ocean?
That is definitely something profound to mull over. Until our next deep dive.